we are going to continue our discussion on PWM techniques. So my plan is to cover a major part of PWM techniques today, and then we will have another class on Thursday so that we complete discussion about PWM. So that's for PWM. Then we will spend one day's class. Okay. Next Tuesday I'll be talking about Chapter 8, soft switching technique. Okay. So only for next Tuesday. And after that, on Thursday, I have one class on, so next Thursday, the Thursday on next week, I'll be talking about applications, power electronics applications. So probably after, I will take two days class talking about applications, and one final class on summary. Okay. So probably we will still have, including today, we will still have 3 weeks, totally 3 weeks to complete the lecturing of this course. So it's almost approaching the end of this course, so I hope you can, if you want, you can start to review some of the contents of this course. All right. So let's see the PWM techniques. We have basically covered the principle of pulse width modulation from last class. As we mentioned, this is all based on the equal area theorem. So based on the equal area theorem, we can actually use a series of same height but different widths, square wave pulses to emulate all different waveforms, as long as we keep the area of each of these square wave pulses the same as the area that you want to the area of the pulse you want to emulate. So that's the basic idea of equal area theorem. So with PWM technique, we can theoretically emulate any kind of waveform we want to emulate. And then we start to talk about the different techniques to implement this PWM idea, pulse width modulation idea. And the first one we started to talk about was sampling, triangular wave sampling method. Okay, and we have actually started to talk about a particular sampling, triangular wave sampling technique, which is called triangular wave natural sampling. And on the right-hand side of this slide, we have already started to talk about the basic idea, basic idea of how to realize this triangular wave natural sampling. Let's make a brief review of what we have discussed in last class. So if this red line is the sine wave you want to emulate, we can use a series of triangular waves. Okay? And pay attention to this particular triangular wave. For when this red line, this modulation, the red line is what we call modulating signal. When this modulating signal is positive, the triangular wave I'm using is also positive. Okay? When the modulating signal is negative, the triangular wave I'm using is also negative. So I'm using this triangular wave to compare with the red line wave. That means the triangular wave is called as carrier signal. The red line is called modulating signal. That means I'm using a carrier signal to compare with modulating signal. When modulating signal is larger or higher than triangular wave carrier signal, I'm generating a positive, I'm using a positive pulse. Okay? And when the modulating signal is smaller than, let's say for this part of time, when modulating signal is smaller than the triangular signal, carrier signal, then I'm generating a zero level, zero voltage. So with this method, I can generate a series of same height but different ways of square wave pulses. So you can see the fundamental idea of this triangular wave natural sampling technique is to use the intersection points between the modulating signal and the carrier signal to determine the leading edge and falling edge instance, leading edge and falling edge instance of the square wave pulses, leading edge and falling edge. Leading edge or rising edge, another name is rising edge. Another name for falling edge. Rising, falling, those are counterparts. And leading edge, another name for falling edge is trailing edge. And the trailing and leading and trailing, these are counterparts. Okay. So the fundamental idea of this sampling technique is actually using the intersection points of the modulating signal and carrier signals to determine the leading edge and trailing edge instance of the square wave pulses. Okay. And in last class we have discussed, we proved that by doing this, using this technique, we can actually get a series of square wave pulses that each of these square wave pulses, has the same area of the area in the corresponding small pulses in the modulating signal. If you still remember, we can separate the triangular wave. This is one triangular wave period. Okay. The triangular wave actually has separate the modulating signal. This is modulating signal UR. This is the carrier signal UC. The triangular wave actually has separated the modulating signal into very small sections of period. And we have proved that the area of this square wave pulse is the same as the corresponding pulse we separated from the modulating signal. As long as, let's see, as long as, pay attention to, we have a condition. As long as we keep the height of this pulse, let's say this is a UD, same as the height of the triangular wave magnitude. As long as this is the same. So we have proved that. So I ask you to do this detailed verification after the class using what you have learned from middle school. Did you do that? We proved that this area should be the same. That would be very interesting. Okay? So this is what we have done from last class. Okay? So we have proved that using, on the right-hand side, using this square wave pulses, series square wave pulses, we can emulate this, in the upper side, the red line sine wave. Okay, now let's see. If we use a single-phase voltage source inverter, VSI, on the left-hand side, we are trying to use a single-phase VSI to implement this idea. Voltage source inverter. If you still remember, voltage source inverter is trying to convert DC energy to AC. Okay? What we have learned before was just to use to transfer, let's say, DC energy to a square wave AC, right? If you still remember, for voltage source inverters, there are three basic features, right? If you still remember, the first feature is the DC side of VSI is usually a constant voltage, either a voltage source or a large capacitor. So the DC side voltage is constant. That's the first feature. The second feature is AC side is usually square wave or quasi-square wave. Okay. And third feature is that there's always an anti-parallel diode connected with a fully controlled device to provide energy feedback paths. So these are the three features for VSI. Okay. What we have learned before was that a voltage source inverter can be used to generate square wave output voltage. So the load will see square wave. Okay, so now let's see how I can utilize this natural sampling, triangular wave natural sampling technique to generate an AC voltage, but not pure square wave. If I'm able to generate a AC voltage like this, that would be much closer to sine wave. That will be very good for many of the loads, because many of the AC loads they require near sine wave voltage. So that if we were still using the square wave voltage source inverter, let's say if we are still generating either 180-degree square wave, so this is the load. If this is the load voltage, this is far from sine wave. If you do Fourier series analysis, they do have fundamental components. Okay, these are the fundamental components, but it does have a lot of harmonics, right? It has third harmonics, fifth, seventh, ninth, all harmonics there. It is far away from sine wave. So that is not good. I want to generate a AC voltage that is more closer to sine wave. But the idea is if I can use this single phase voltage source inverter to generate an output voltage like this with this waveform, this would be much closer to sine wave. Okay. We want to generate a PWM output voltage. Okay. So let's see, how can we implement this PWM natural sampling idea in this single phase voltage source inverter? Looks like it's not difficult, because if you look at the lower side on the lower right hand side waveform, the output waveform we want to generate is just, let's say, positive pulse 0, positive pulse 0. Okay, for the positive half cycle, what we need to do is generate positive square wave 0. So these two levels of output voltage. And for the negative half cycle, what we need to do is generate 0 and negative level of output voltage. Okay, so let's see, how do we generate positive output voltage? If you still remember what we learned from the chapter of inverters, we should know, as long as we send turning on signal to V1 and V4, the voltage across the load will be exactly positive UD, right? As long as we send turning on signal to V1, V4. The left-hand side of the load will be connected with the positive terminal of the DC side, and the right-hand side of the load will be connected with the negative terminal of input voltage. Therefore, the load voltage will be positive UD, exactly. It doesn't matter what direction the load current is. Either load current could be either flowing from left to right or flow from right to left. Either way, the load voltage will be positive UD. Okay? So as long as we send turning on signal to V1, V4. And because in the same half bridge, we always control, for voltage source inverter, we always control the devices in the same half bridge in a complementary manner. So when we send turning on signal to V1, we send turning off signal to V2. When we send turning on signal to V4, we always send turning off signal to V3. So that's clear. So how we generate this positive UD output voltage. Then I'm asking, how do we generate this zero output voltage? Is it clear? There are two ways, right? Two ways to generate this zero output voltage. What is it? I can either send turning on signal to V1 and V3, right? As long as I send turning on to V1, V3, then the left-hand side of the load and right-hand side of the load will be connected together through this point, right? It doesn't matter the current will be flowing in which direction. Let's say, let me get a little bit into the detail in case you don't memorize what we have discussed before. Okay, so if the current is flowing from left to right, then it must be V1 load VD3. The current should be flowing this way, from left to right. Okay? If the current is flowing from right to left, then it would be flowing from right to left. Let's see, right to left. It should be flowing through the load VD1 and V3 coming back. So the current will be flowing this way. No matter which way it is, the load left-hand side terminal will always be connected with right-hand side terminal through this either V1, V3 or VD1, VD3. And therefore the load voltage is always zero. Okay? So that is one way. What is the other way? I can send turning on signal to V1, V3 and send turning off signal to V2 and V4. What is the other way? The other way around, right? Send turning on signal to V2 and V4, turning off signal to V1, V3. So I have two ways to realize this zero output voltage. Okay? So for positive half cycle, I can do that this way. And similarly, I can do, let's see, for the negative half cycle, I have to generate, okay, negative UD and zero. Okay. For zeros, we have already mentioned. So there are two ways to generate zero output voltage. But how do we generate negative UD? Well, of course, this is also clear. As long as I send turning on signal to V2 and V3, I send turning on signal to V2 and V3 and turning off signal to V1, V4. Then the left-hand side of the load will always be connected to the negative terminal of the input through V2 or VD2, no matter which one it is. The left-hand side always connected to negative terminal of input. The right-hand side will always be connected through V3 or VD3 to the positive terminal. Therefore, the load voltage is negative. So this is the way to generate the output voltage we want. We can, through this control, to generate a series of square wave pulses you want to make the output voltage much more closer to sine wave. Okay? One more question. Let's think about one step further. In the control circuit, how do we implement this idea? Okay. To turn on V1, V4, or V2, V3, any one of these. In the control circuit, how do we implement the control of the control of the four power semiconductor devices so that we can generate the PWM output voltage we want. Okay. So far, we have been always talking about when this happens, okay? At this instant, we want to turn on, let's see, V1, V4, and then turning off signal to V2 and V3. Okay, and then after that, for this section, when we want to generate 0, we said we can send turning on signal to V1 and V3, turning off signal to V2 and V4. This is all idea. And how do we automatically implement this idea in a control circuit? Okay, of course, by digital control. If you are using a microcomputer to do digital control, this is all realized by a program, software program, right? You can always realize that. When this instant comes, you send turning on signal to the power semiconductor devices you want. If I'm using an analog control circuit, how do we automatically generate these turning on signals and turning off signals for all these 4 IGBTs, all these 4 power semiconductor devices? How do we do that? Okay. How do we automatically generate those gate control signals for these 4 IGBTs in the control circuit? Okay. There are many solutions, actually. You will figure out later. There are many solutions you can realize this control. You can generate the gate signals for the 4 IGBTs. Here I'm going to show you just one solution, okay? One solution to realize this idea. Okay? In the control circuit, I want to, let's see, in the control circuit, I want to use a sine wave. I generate a sine wave. This is all in the control. A sine wave and a series of triangular wave. That's the carrier with the same carrier frequency. This is another wave. And then I send this to a comparator. This is a comparator. When I compare these two, that means when the modulating signal is larger than the triangular carrier signal, then the output will be positive. And when that is smaller in the reverse direction, then that will be zero. Okay, let me do this. Let me do this. When this is higher than this voltage, through this comparator, I generate a high-level output. When the modulating signal is smaller than this, through this comparator, and I generate a zero output. Okay, so this is one output. Okay. Okay. I use this signal to control, to send this to V1. Use this signal as the gate control signal to V1. Okay? Then I use, let's see, an inverter. Or NOT gate. To generate exactly reverse direction output. Okay? So when this is high level, this is low level, 0. Okay? When this is a low level, and this is high level. Exactly reverse. Okay? I'm using this reverse direction of signal as the signal for V2. Because these two, V1, V2, should be controlled in a complementary manner. So when I turn on V1, I have to send a not turn on signal, that means turn off signal to V2. Okay? I can do that. And then for V3 and V4, how do I do? I say for the positive half cycle, when you want to generate, let's see, positive PWM pulse, I'm also generating a square wave. Okay? And this square wave is used as the signal for V4. I use this signal, same phase angle square wave signal as the modulating signal to control V4. And then at the same time, I'm also using a NOT gate to reverse the direction of this signal, and therefore use this as the gate signal for V3. Use this to control V3. In this way, I can realize this output voltage I want. Why? Because this comparator is realizing its natural sampling. When the modulating signal is higher than the triangular signal, I'm turning on V1. Okay? And for the positive half cycle, upper cycle, I'm also turning on V4. So for the positive half cycle, V4 is always conducting, either V4 or VD4. Can you follow me? For the positive half cycle, I set V4 always be conducting. Okay, and therefore, whether the right-hand side of the load will always be connected to this point. So whether the load will see positive voltage or zero voltage will depend on whether this V1 is, whether you are sending turning on signal to V1 or turning off signal to V1. So when both these two the gate signal for V4 and V1 are positive, then you are outputting positive voltage. And then when, let's say, V4 is positive, I'm sending turning on signal to V4, and V2 is turned on. You're sending turning on signal to V2. That means you are sending turning on signal to V2 and V4. That means you are generating zero output voltage. Okay. So through this way, I'm really implementing this PWM output voltage idea. Okay. This is one solution, as I said. There are many other solutions. You can figure it out. Actually, the second course project will be assigned to you later. It is all about how you realize a PWM control for a voltage source inverter. Okay, and you figure out how you can implement this idea in the control circuit. So what is the bad thing about this is V4, let's say for half cycle, output voltage half cycle, V4 or V3 is always turned on or turned off. That means the requirement for V3 and V4 is different from the requirement for V1, V2. So this is not good. When you design the actual power converter, you have to select different power semiconductor devices for V3 and V4. Okay, so that's the disadvantage of this solution. And you can figure out a better solution than this. You can figure out a solution that can realize V1, V2, V3, V4, they are working under an evenly distributed condition. And these four devices can be selected under the same requirement. Okay? And in the end, I have to point out that this sampling technique. That means when the modulating signal is positive, I'm using also positive triangular wave carrier signal. When the modulating signal is negative, I'm also using negative modulating signal. This technique is also called unipolar sampling. Unipolar sampling. And the emulating PWM waveform, you can see, is also, for the positive half cycle, this is also one direction, positive direction. For the negative half cycle, all these square wave pulses are negative direction. So this PWM is also called unipolar PWM. Okay. So you can see unipolar sampling is used to realize unipolar PWM. Okay. And we can also figure out that we can generate another type of pulse width modulated output voltage. You can see in this page. On the upper side, upper right-hand side, you can see this time I'm still trying to emulate this red line sine wave, but this time I'm not using unipolar triangular wave. I'm using bipolar triangular wave. That means even within the positive half cycle, the triangular carriers are bidirectional. Okay? So this is called bipolar sampling. Okay? The modulating signal is comparing with a bipolar triangular wave. Okay? But the idea is similar. The intersection points between this modulating signal and carrier signal determine the leading edge and the trailing edge of the square wave pulses in the lower side, you can see. But the difference between this one and the previous one is, let's say when the modulating signal is higher than the triangular wave signal, I'm generating positive pulse, so positive level of up voltage. And when the modulating signal is smaller than, let's say for this part, smaller than the carrier signal, I'm generating a negative output voltage, not zero. Remember, in the previous case, when the modulating signal is smaller than triangular wave signal, I'm generating zero. But in this case, I'm not generating zero, I'm generating negative. So the actual PWM waveform I want to generate is also bipolar, either positive or negative. Positive or negative. There is no zero level. No zero level. I can also prove this technique. If I'm doing this, this is also following the equal area theorem. I can also do that. I'll show you the basic idea, but I want to encourage you to do that after the class in detail. Let's see, this is the triangular wave. One period of triangular wave, bipolar triangular wave. So this, let's say this is the zero line. Okay? This is UC, carrier triangular wave. And then you have this modulating signal. This is UR. And because this one period of triangular wave is very short, so I always assume this modulating signal is constant, does not change within one triangular period. Okay. Then this sampling technique, basic idea is that the intersection point, this is the one point, this is another point. This intersection point actually determines the leading edge and the trailing edge of the square wave pulses. There's no red chopsticks anymore. Okay. Maybe let me use the green one. These two intersection points determines the leading edge and trailing edge. When UR is higher or larger than UC, then I'm generating positive output level. And then when, let's say for this part, UR is smaller than UC, therefore I'm generating negative. See. So this is the output voltage. As long as what? As long as the magnitude of the square wave pulse is the same as the triangular wave pulse. Let's say this is all UD. Let me use UD to represent the magnitude of triangular wave and this square wave pulse. to make it looks like the same. Okay, so this green line, green pulse, is the pulse I'm generating. So I can prove that the area of this green pulse, square wave pulse, is the same as what? Same as this part. Same as the corresponding pulses separated from this sine wave. So I'm trying to prove that the area of this green pulse is the same as the area of this shaded area from the sine wave, right? That's what I want to prove. If I can do that, then that's following the equal area theorem. Okay. Then you can actually prove. Okay. What is the area? What is the area of this square wave pulse? The square wave pulse has this part, actually. This is the area when this pulse, square wave pulse, is positive. Okay. This is one part. Okay. That's the square wave. But it also, pay attention to this, it also has a negative part. This is negative pulse. Okay. There's also a negative pulse on the right-hand side. Okay. You can prove after the class that for this green part, green pulse, the positive pulse area minus these two negative part area will be exactly equal to this sine wave pulse. Sorry, did I read it wrong? Here. Sine wave should be this is the sine wave. The positive green pulse area minus the negative green pulse area will be exactly equal to this white shaded area from the sine wave. Prove that after the class. Again, use your knowledge from middle school. Okay? So by doing this, I can generate a series of square waves to emulate sine wave. But in this case, this a series of square waves are bipolar. So just positive, negative, positive, negative. So just these two output voltage levels. So this is called bipolar sampling because I'm using bipolar triangular wave to compare with modulating signal. So bipolar sampling is used to realize bipolar PWM. Okay. Well, the actual control to realize this bipolar PWM output voltage for a single phase voltage source inverter is actually much simpler than the previous one. Because in the previous one, I have to generate positive, 0, negative, this 3 level of output. And in this case, I do not want to do that. What I need to do is only generate positive voltage and negative voltage. There's no need to generate 0 voltage. So this is simpler. So you can probably come out in an idea, how do I, in the control, similar idea. In the control, how do I control this V1, V2, V3, V4? How do I generate these gate signals for these 4 IGBT devices so that I can generate this series of bipolar PWM output voltage? So this is your job to figure it out. So through this course project. Okay. But there's one thing I want to point out before we take a break. Pay attention to this. From the idea, from our verification, provement, we can see that bipolar sampling, that means using bipolar triangular waves to compare with modulating signal, can only be used to generate bipolar PWM. So the PWM voltage you want to generate should be this bipolar waveform. And therefore, unipolar sampling technique can only be used to generate unipolar PWM waveform. We cannot do in another way. Unipolar sampling cannot be used to generate bipolar PWM. Or bipolar sampling cannot be used to generate unipolar PWM. Because this is all based on this equal area, based on equal area theorem. So pay attention to that. Take a break.